Hey, welcome folks to another video in our thermochemistry series where we're going to talk about and build on a previous lesson where we looked at Hess's law. And Hess's law simply states that when you look at the enthalpy change of a reaction, what is important is the beginning and end states, and it's not so important what happens in between. And Hess's law, we looked at manipulating equations and enthalpies to arrive at the overall enthalpy for a reaction if we look at the intermediate reaction enthalpies. But there is a second way to do it, and that is looking at standard enthalpies of formation. Now on the diagram I've put a little Lego block, Lego wall, and that for me represents a kind of a metaphor for standard enthalpies of formation. Standard enthalpies of formation, basically put simply, is if we look at the individual blocks, blue blocks, yellow blocks, red blocks that make up the wall, and we understand a little bit about those, we can piece that together to look at the overall structure of the wall. Similarly, we can look at the overall structure of an equation. So standard enthalpies of formation. Reactions in which compounds are formed from their elements are reactions or enthalpies of formation. And these are normally known values which have been calculated, in which it was easier to calculate those formation values than to calculate the value that we're looking for in this instance. And these standard enthalpies of formation are always written for 1 mole of product, not reactant, product. So in this case on screen it would be 1 mole of carbon dioxide. So that's why it's negative 393.5 kilojoules per mole. It is also always written when the reactants are in their standard states, and that's standard atmospheric temperature and pressure. So we got to have standards, we got to have reference points, and these reference points that we're going to set generally is 25 degrees Celsius and 100 kilopascals. So standard temperature and pressure. And the standard enthalpies of formation of elements are always 0. Now we should also note that these are for elements in their most common state. So if we look at the bottom corner here, what we're talking about, of course, is diatomic oxygen and not the single atom oxygen or indeed ozone, because O2 is the most common state. So the standard enthalpies of formation of elements are always 0. So we're just going to look at an example. We can use standard enthalpies in the following equation to determine the enthalpy of reaction. So what we do to get the enthalpy reaction is we look at the sum of the number of moles of the enthalpies of products, and we take away the sum of number of moles of enthalpy of reactants, just like the equation in the box. So we're just going to look at a sample problem here. Calculate the enthalpy change for the following reaction using standard molar heats of formation. Okay, so this might be one of those instances where it's actually very difficult to find this in any other way, but we do have a way, which is to look at the enthalpies of formation of ammonia and chlorine, nitrogen and hydrochloric acid. So if we look at this, we can look at the enthalpy of the changes of the products, and we can take away the enthalpy change of the reactants, and hopefully we can see using the example at the top here. Okay, so the standard enthalpy change for ammonia, and this is something you can look up, you can search it looking on the internet and so on, is minus 45.9 kilojoules per mole. Similarly for HCl, we have the value, and for Cl2 and N2, those gases, well, they're elements, and so their enthalpy of formation is 0. If we use our equation that we previously talked about, we will get a value of negative 461.2 kilojoules. Now it is important to note at this stage that we need to multiply the second equation, enthalpy of formation equation, by 6 because there was 6 HCl produced in the product, and we need to multiply the top equation, the ammonia, by 2 because the coefficient beside ammonia in this equation up here was 2. So it's important that we multiply it by 2. It is also important to note the signs involved. So when we have a double negative, it's going to change it, obviously. So what we need to next figure out is, and maybe ask ourselves, is what type of a reaction is this? Is it going to give off heat? Is it going to absorb heat? Is it exothermic or endothermic? Maybe you can stop the video and just decide. Well, the presence of the negative sign here tells us it's an exothermic reaction. That means that it's going to kick out energy, give off energy to the surroundings. And of course, if we had something to measure that, like our hand, for instance, or a sensor of some sort, we would see a temperature increase in the surroundings. So don't forget to multiply by the number of moles. Sample problem 2. What's the molar enthalpy of combustion of methane fuel? You would have to look up the standard molar enthalpies of formation. So you'd have to do a little bit of dig work. You'd have to get that, magnifying glass out, get on the interweb and get moving. And you would find some values here for carbon dioxide, water, oxygen, and methane. And you have all that you need now to answer this question. Bearing in mind you understand what the products are and what the reactants are, keeping in mind the coefficients actually mean something. So that's a problem that you can work on, you can figure out, and hopefully you can get the value for. And there's another sample problem for you to work on here. Again, you can look up the standard molar enthalpies. I've put those on screen, and hopefully you can figure out that problem. So this was just a video showing how to use standard enthalpies of formation to find out the total overall enthalpy of a reaction. Hopefully that helped you out. If you found this video useful or interesting, just give us a wee thumbs up, please.